Okay, so last time we went ahead and tackled polar coordinates, and now we're going to extend into 3D. It turns out, if you go into graduate school, you'll eventually learn the little bon mots that there are 11 coordinate systems in which the Laplacian separates. And one of your professors might be cruel enough to make you do something in one of the ones that's not one of the big three. But 99 and 44/100% of all systems you'll ever analyze will either break down nicely in Cartesian, cylindrical, or spherical coordinates. Of course, there will be that one time where confocal hyperbolic coordinates is really the way to go, but when the time comes, you'll be able to pick that up for yourself. So anyway, we'll go ahead and start with cylindrical. We will start with cylindrical coordinates. Okay. So again, remember all of our differentiation has to be done in reference to Cartesian. So I'll go ahead and plop down an XYZ coordinate system. And we're going to leverage off of just kind of the same way that we were doing things in plane polar coordinates. So let's say that this is my point of interest right here, and I need to locate it. So just for quick reference again, here are our Cartesian unit vectors I, j, and k hat. They'll never move, they'll never change their orientation. Now if this is, say, my location here, it turns out that for me to define some cylindrical coordinates, my unit vectors will be, first I will, if I imagine just dropping a perpendicular off the z-axis and going across, the unit vector that follows that out, that's r hat. The one that's parallel to k, we usually call that z hat, but z hat and k hat are equal. We'll touch on that in a moment. And then we need one to complete the triad. Now the way we can kind of take that along is if I go ahead, drop this down to the xy plane, then this distance here, yeah, that came out really nice here. Let's make that look a little better at least. Much better. Then this distance here is my capital R, and this angle here off the x-axis is phi. So again, we're going in a counterclockwise-y kind of direction. So then, here, let me redraw r hat and make that look a little better. There's a better looking r hat. Then mutually perpendicular to all those is phi hat right there. Okay. So my position vector, in analogy to what we were doing with polar coordinates, we will get how far, remember here, the r hat vector moves with my point of interest. So it just tells me how far away to go from a perpendicular off the z-axis. And I just go in which direction? The r hat direction. So it'll be r hat. And on top, so that gets me to say here, and then I need to go up some height z. Oh, we can make that look better. So we can go up some height z, like so. So it'll be plus z hat, and that's it. It'll never have a contribution from phi hat because it doesn't make any sense for a position. Our z hat just gets me up to where I need to be. R hat points me away from the z-axis, and remember the unit vector changes direction depending on where you're located, so it always points the way you need it to. Okay, so we want to compare our unit vectors with respect to Cartesian in case you need to go back and forth between the two. So the low-hanging fruit is that z hat and k hat are absolutely equal. R hat, we're going to get, well, if we project onto the x-axis, we see that will be the cosine of phi times I hat plus the sine of phi times j hat. And similarly, phi hat, everything being rotated around here, we will get that that is minus sine phi I hat plus cos phi j hat. So if you need to go in and out of Cartesian, that's how to do it. But once again, I would really suggest you try to avoid doing that if you can help it. So again, leveraging off of what we know for plane polar coordinates, if I want the velocity of something, so that's r dot. Following just what I had before, that'll be r dot r hat plus r hat, sorry, r hat dot, so that's half of it, and then I need to do a plus z dot z hat, differentiating this bit, plus a z hat dot, but that last bit there is going to give me 0 because the z vector never changes direction, it always points up. And obviously it can't change length because it's a unit vector. Okay, so that's all better there. So that drops out. And so we have these three pieces left. Now, as before, so r dot r hat, like so, our hat dot is going to be equal to phi dot phi hat, just like before with plane polar. And if we needed it, phi hat dot would be equal to minus phi dot r hat, but we don't need that here. And then we're just left with the z dot z hat, so that's it. Okay. And if I want the acceleration, okay, that's going to get a little uglier again. But usually you're picking these coordinate systems because there's something about the force law or something like that that's going to make a lot of the ugly cross terms drop out. And so this will actually, in practical problems, will be easier to analyze. So A equals R double dot, which would be the same thing as V dot. So we'll take this result here and differentiate it, and we'll follow that through. So this will give me two terms. I'll get an R double dot R hat plus R dot R hat dot, plus this will give me three terms. I'll have an R dot phi hat plus R phi double dot phi hat plus R phi dot phi hat dot. Then we pick up from here z double dot z hat plus z dot z hat dot, but that last one again is 0 because z hat never moves. Okay, so once again we have to pay attention to the r hat dot. So remember, r hat dot we worked out was phi dot phi hat from when we worked in plane polar, and by the same token phi hat dot would be equal to minus phi dot r hat. So we'll just go ahead and put those in. So my acceleration becomes r double dot r hat plus r dot phi hat plus r dot phi hat, oh that's convenient, plus r phi double dot phi hat plus r phi dot, and now we'll have this minus phi dot r hat, so that's going to make this plus a minus. We'll square that and give me an r hat from that term plus z double dot z hat. I can clean this up just a little bit to get that the acceleration will be equal to r double dot minus r phi dot squared r hat plus 2 r dot phi dot plus r phi double dot phi hat plus z double dot z hat. Okay, now this looks really bad, but keep in mind that you would be applying this, say, like looking at the analyzing the trajectory of an electric charge near a very long wire. So you'd have some sort of cylindrical symmetry from that. So the force vectors would only point in the r hat direction in this case. So that would make our double dot terms non-zero, and everything else would our r dot and r double dot would be 0, or non-zero, and our phi dot would be non-zero, but our phi double dot would be 0, and our z double dot would be 0. And so a lot of these terms would drop out and would actually be much simpler to analyze than it looks in general. Okay, now on to spherical coordinates. And here, unfortunately, the physics community has a difference in notation with the math community. Don't shoot the messenger. The two fields really have crystallized in what they do, and unfortunately you just have to live with it if you're moving back and forth between math and physics texts. So again, I go ahead and put in a Cartesian coordinate system, and we'll mark the Cartesian unit vectors just like before. Okay, so now we're not going to have a z hat that's parallel to k hat. We're just going to take everything straight off from the origin. So there's my point off from the origin. So if I draw a line that extends off from the origin, my r hat will point straight off from the origin like that. Okay. The next angle we care about will tell us how we get off, and sorry, this length here is r. This angle here, actually let's do it like this. This angle here, theta, gets measured off of the z-axis. In math class, this usually gets called phi. Physicists call it theta. It's been that way basically since day one, and that's just the way it goes, unfortunately. So anyway, my theta hat will follow that direction off of the z-axis. Then finally, to get phi hat, they'll be just like the phi we were doing in, they'll be just like the phi we were doing in cylindrical coordinates. We go ahead, drop down to the xy plane, and this angle here off of x, counterclockwise off of x, is my phi. So theta and phi are reversed from your math class, and I'm sorry, that's just how we roll. So, pardon the crappy art, this is pointing more into the page. This is pointing off of the r hat. This is pointing down. So the right-handed trio is r, theta hat, phi hat in that order. Okay, if ever you need to go convert into Cartesian, r hat is going to work out to be, well, to get the I hat component, I'm going to have to take that and times it by the sine of, times it by the sine of theta. And then I'll have to take, to get this length here, so this length right here, that would be r times the sine of theta. And then to get this length over here, I'd have to multiply that by cosine phi. So it'll be equal to sine theta cosine phi I hat plus sine theta sine phi j hat plus cosine theta k hat. Similarly, you can show that theta hat would have to be cos theta cos phi I hat plus cos theta sine phi j hat minus sine theta k hat. And then finally, the phi hat piece, there's nothing directed along r, nothing directed along k hat, at least for what that's worth. So it would just be equal to minus sine phi I hat plus cos phi j hat. Alrighty. Well, in any event, let's go ahead and start working on our unit vector derivatives here. And here I think I'll do it by the whole, let's differentiate the Cartesian coordinates and see what happens, just to show that yes, we can do it that way if we have to. So r hat dot, let's think about that. Well, r hat is this whole bit right here, so now I'm going to need to differentiate that. And at least what's nice about using this method is the i's, j's, and k's. When you differentiate them, you just get 0, so we don't have to worry about them. So we will be left with, okay, differentiating sine theta will give me cos theta times the derivative of what's inside. Gives me theta dot, cos theta cos phi. Then I have to do the next one here, so I'll have a sine theta derivative of cosine is minus the sine, and then differentiate what's inside will give me a phi dot, so minus phi dot sine theta sine phi. That's just the I hat piece. And then we go ahead, Similarly, we'll get the j hat piece differentiating this. We'll pick up two terms, and those two terms will be theta dot cos theta sine phi minus phi dot sine theta cos phi j hat. Then lastly here, derivative of sine is cosine. So the derivative of cosine is minus the sine. So we're left with minus theta dot sine theta k hat. Okay. Well, three of these terms all have a theta dot in front. Two of these terms have a phi dot in front. So let's pull them out separately, huh? So this will become theta dot times cos theta cos phi I hat plus cos theta sine phi j hat minus sine theta k hat plus there's a bit with phi dot, so let's pull it out. I'm sorry, I dropped a minus sign there when I was differentiating. So pulling that out, I'll get a phi, doggone it. I will get a phi dot, and I can group out a sine theta. For what it's worth, I'll be left with minus sine phi I hat plus cos phi j hat. Well, I look at this. This whole long-winded complicated thing is just plain theta hat. So we get theta dot theta hat for r hat dot plus this bit here is phi hat, so I get a phi dot sine theta phi hat. Excellent. Similarly, we can do theta hat dot and you will get that it is minus theta dot r hat plus phi dot cos theta phi hat. You should either convince yourself by trying to do small differential moves in the theta hat along the theta hat direction and see what happens, or by going ahead and gutting it through in the Cartesian coordinates. And then finally, by the same sort of process, you should be able to convince yourself that phi hat dot is equal to minus phi dot sine theta r hat plus phi dot cosine theta theta hat. Okay, those last two look really ugly, but again, you're going to be picking this coordinate system probably because you have a central force law. So something like the gravitational or the electric force. So really all the action is going to be happening mostly along r, especially when we get to the acceleration. Okay, so we can get the acceleration the same kind of way. The acceleration is equal to v dot. So we go ahead and, oh, I'm sorry, I forgot to finish up here. Let's finish up getting the velocity. So for our velocity, v, which is equal to r dot. Okay, keep in mind that r, going way back here for my, oops, not too far back though, that my position vector here is just going to be this length r times r hat, because that's all I need to tell me how to get to the location. Now, of course, r hat depends on where I'm located, but since I already have my r hat somehow, I just need to know that I go r away from there. So we'll just start with saying that in spherical coordinates, my position r is equal to r hat. And that's it. So to get the velocity, that's just going to be r dot. So it'll be r dot r hat plus r hat dot. Well, we just worked out what r hat dot is. It's this stuff here. So we'll go ahead and put that in. So this becomes r dot r hat plus r theta dot theta hat plus r phi dot sine theta phi hat. All right. And then to get the acceleration, so the acceleration will be what we get when we differentiate that. So, okay, we're going to be getting a bunch of terms, and it's going to look a little ugly, but again, keep in mind, when you pick a coordinate system like this, you pick it because a lot of what will look like ugly terms in this will actually be 0. So differentiating this, I'll have an r double dot r hat plus r dot r hat dot, plus this will give me 3 terms, so r dot theta hat plus r theta double dot theta hat plus r theta dot theta hat dot, plus get 4 terms out of this bad boy. Sorry, that's just the way it goes. So I'll have an r dot phi dot sine theta phi hat plus r phi double dot sine theta phi hat. Now differentiating the sign, we gotta be a little careful. Derivative of sine, remember, is cosine, but we also have to worry about the derivative of what's inside. So we end up with r r phi dot theta dot, derivative of sine is cosine theta phi hat, plus finally r phi dot sine theta phi hat dot. All right. And once again, you will substitute all of these guys in. You can, when you do that, it's not going to get too terribly clean. So I'll just say when you substitute and you clean it up a little bit, you're going to get an r, you're going to get an r double dot minus r phi dot squared sine squared theta minus r theta dot squared r hat plus r theta double dot plus 2r dot theta dot minus r phi dot squared sine theta cosine theta theta hat plus r phi double dot sine theta plus 2r dot phi dot sine theta plus 2r theta dot phi dot cosine theta phi hat. Now again, all this looks absolutely hideous, but keep in mind that at the very least, you're probably picking this coordinate system because theta double dot and phi double dot will be 0. And probably your initial conditions will make some of these other things, like maybe the phi dot be 0 or something like that. And so you'll only be left with a handful of these terms. They'll be much more tractable and probably work out a lot better than if you attempted to gut this all out in spherical coordinate, in Cartesian coordinates. Okay. Now, in the text, you probably worked through, if you haven't, you should, example 1.12.2. It's worth noting there's a typo. If you look in the text, it says r dot equals blank equals 0. The thing that should be going in the blank is r double dot, for what that's worth. So just watch out for that typo there. Now, it's worth doing a bit of an extension off of that example, so let's just do that. So we can ask, what is the speed of the point on the top of the wheel? So we want the speed of the point on top of the wheel. Now, I would recommend here that if you haven't familiarized yourself with this example, this is probably a good time to go pause the video, work through the example that they had, and then go ahead and unpause this and we'll finish it out. So we have from before that the velocity would be r dot r hat plus r theta dot theta hat plus r phi dot sine theta phi hat. Now putting in what those things are, r dot has to be 0, right? The radius of the wheel doesn't change, so that term drops. Now, we said that the radius of the wheel was b, so this will be b theta dot would be omega 1, that'll be in the theta hat direction, and then phi dot, the precession angular frequency, so this will be plus b omega 2 sine theta phi hat. Okay, so now if we're at the top, though, theta is 0, so that will make the sine of theta 0 at the top. And so we get that the speed, v, since this is a unit vector, the speed will just be b omega 1, which I hope squares with what your intuition was for the problem. Okay. Next time we will start delving into Newton's laws of motion.